Okay, moving on from internal resistance and EMF, the rest of chapter 5.3 will simply be charging and discharging the cell, which is, you can see it's not a lot of content here. So I think it's the best if you can check the expectation from the study guide, and I think this is something that you should do also whenever you feel confused in any kind of subjects you have. So here is the study guide, so let's go through them. This is 5.3, and we talk about cells, internal resistance. Secondary cells is something that we will talk about later on, and basically is, I don't know why it's called secondary cell, but it's basically it's kind of a battery that can be recharged and used again. And I don't know whether it's still common nowadays, because I think what you would have instead would be more like the lithium battery in your cell phone. But actually in the past there are some rechargeable battery simply, which looks exactly the same as others, like those battery in your remote control, but they can be recharged somehow, and we just call it secondary cells. We'll talk about that later on. Terminal potential difference, of course, we talked about that in the previous video. EMF, yes, we did. Investigating the cell for both primary and secondary, so we can actually somehow set the battery in opposite direction. So if you try to look at these circuit on the right hand side here, you see it's very simple when we talk about charging cell. So you can see that this is 12V. Maybe I use a pen, let me try. This is 12V, and then this is 2V, and apparently the dominant one is 12V because it's simply higher. And so these will set up the direction of current. And then when you see, when the current go into this, the direction of the battery is having positive here and negative here. And let's not forget, normally for the current, let's say 12V, that one, when the currents go back to the cell, it should go in from the negative and go out from positive for conventional current. And so what happened is, when you have that conventional current going into this 2-volt cell, you are actually giving energy to the cell instead of taking energy from the cell. If you remember the analogy of maybe the circuit as people are buying stuff, then the cell is like the bank. People, which are the electron carrying the energy, which are the money, and the money was taken from the bank, which is the battery. So what happened here is, this is a much bigger bank, and somehow the orientation of the cell, which is the bank itself, in this case, people, when they pass through this bank, they actually put money back to the bank here instead, because of, again, the orientation. So this is what happened when you put the cell like this. However, there are some cells that are not rechargeable, and even if you put it this way, you cannot charge them. So you simply have to check the nature of the cell itself. That involves something to do with chemistry, whether the chemical reaction is reversible or not. Then it will be able, then you can see whether it's rechargeable or not. Okay, so the next thing is about describing the discharging characteristic, which we will talk later on. The direction required to charge a cell, yes, that's exactly what we did. And finding out the internal resistance experimentally, which is the previous part 2 experiment, part 2 video I should say. Solving problem involving EMF, internal resistance, and other quantities, yes, that's something that we did, and we will do more in the next video on some more questions as practice. For guidance, it said students should recognize the terminal potential difference of typical practical, well, that's very complicated, loses its initial value quickly and has a stable and constant value for most of its lifetime, and followed by a rapid decrease, blah blah blah. Okay, very complicated, isn't it? Actually, it's very simple if you look at this graph. Alright, this is basically what it says, and I think that's basically finished the whole, understanding the concept of what you need to learn in this part of video. Is that when you discharge a cell, That means like normal battery, like your remote control. When the battery was fully charged, like new you may say, then at the beginning the voltage may be quite high, and then quite quickly it will drop to a constant period like the blue line here. So most of the time you have a very steady constant amount of voltage under, of course, if the voltage is constant, then current should be constant, all right, assuming you put the battery at the same place. And when the battery is almost used up, or you may say it's almost dead in a more layman term, then the voltage will drop very quickly. And so that's why if you ever have some experience in using battery, again, it's not talking about the lithium battery in your phone, it's more about those very traditional battery, like finger like, should I say that, battery, where you may put in the remote control, or if you ever put a toy car, then you'll find that when the battery is almost dying, then the car would not be moving as fast, but it's still moving, but it's not moving not as fast, and that's because the voltage actually got dropped in that case. And that's exactly what is set for this long sentence here. Okay, and the idea of how to understand these three lines, the blue and the red and the green lines here, is you can see there are three currents, and the blue one will have a relatively less current, 0.5, and the green one is like the highest, 1.5. So imagine you have the same battery, and you can think about a battery is simply like a bucket of water inside, and those water is basically the energy. So energy is like the water. If you poke a hole here, then it will leak, all right, and over time all the water will be out, just like all the energy will be gone from the battery. And depending on how big your hole is, then maybe you have different flow rates, right? That means the current is different. And if you simply have the flow rates to be faster, like this one, with, for example, a much bigger hole, then the water can be, lost in much quicker time, and that's why you can see the time it takes is much shorter. And while the blue one, which is a relatively lower current, then it may take about three times more of the time, I think, right? This is like 150 and this is like 450, yeah, so about 3 times of the time here, because the current is 3 times less in that case. All right, so I think that should be very easy for you, and I think that's pretty much it for this video. In the next video, I'll ask you to do some questions in the question booklet.